Sup YouTube. Today we continue talking about Maxwell's equations. We continue our discussion with Maxwell's third equation, which is known as the Maxwell-Faraday equation, or better known to us as Faraday's law of induction. So just like the previous ones, we first talk about the differential form of the equation, which looks somewhat like this. Del cross E is equal to minus d partial b by dt. Now I'm pretty sure we are familiar with this symbol. Del cross means the curl. We talked about this. Now this symbol, I don't think it is very familiar to us. We are familiar with the regular derivative symbols, d by dt or d by dx. Now this curvy kind of d, basically what it represents is it represents the partial derivative, and that means that when we are differentiating this value, whatever this would be, the b field, when we are representing with a when we are differentiating it with a particular variable, case in point time, at that point all the other variables which this field depends upon, we have to keep them constant. Yes, so this B field may depend upon various different variables. It may vary in the x direction and it may vary in time. So when you are differentiating with time, you have to keep the x variable part of this field as constant. That is what it means. So to interpret this equation, what it says is the curl of the electric field, the E, curl of the electric field is equal to rate of change of the B field with time and opposite in direction. That is what the negative sign signifies. So I'm pretty sure every single one of us has heard the name of Michael Faraday. Yes, and he was one of the greatest physicists of our times, and he started experimenting with circuits and magnetic coils together way back in the 1830s. So his experimental setup as such, it's a pretty simple setup, which is what I'm going to show over here. So he took a battery. Yes, this is the circuit diagram, circuit symbol for a battery. I hope you all know about this. And he took there was a switch, and there was an ammeter connected in series, and he took a coil of wire in which there was a core of magnetic material. He used iron. Okay, this ring thing is the core. So pretty simple experiment. So from our intuitive knowledge, when the battery is disconnected like this, we have no electric current flowing through the wire, which means that there is no magnetic flux induced within the iron core. So why are we using an iron core? So basically ferromagnetic materials like iron, they act like a sort of a highway for magnetic fields. Magnetic fields can flow very easily through ferromagnetic material like this. So the purpose of the core is to create a path for the magnetic flux to flow. So now when the switch is closed, you see the electric current is going to start flowing within the wire attached to the battery. Now when this current is flowing, it is going to have an associated magnetic field or a magnetic flux with it, which is what we talked about when we were talking about the B field and H field, I think in episode 2, I guess, I'm not sure. So when the wire is wrapping around the left side, the wire that is wrapping around the left side of this magnetic core over here, a magnetic flux is going to be induced within the core. So the flux is going to travel around the core, isn't it? Because as we saw that the magnetic fields, when there is a current I which is flowing like this, the H field, it tends to go something like this, right? And we use the right hand thumb rule to check its direction. Its direction is also going to be like this, isn't it? So when we have a coil of electric current, the magnetic flux, as you can see, it's going to be straight. Yes, the direction is going to be linear. So a magnetic flux is going to be induced within the core, which is going to travel around the core, which means that the magnetic flux produced by the wired coil on the left, it is going to exist in the wired coil on the right, isn't it, which is connected to the ammeter, because the left coil is not connected to the ammeter, the right part of the coil is. Yes, so now what happened when Faraday actually did this experiment, it was pretty funny. So when he closed the switch, the current, it would start flowing, and the ammeter would spike one way or the other. So suppose it measured say positive 2 amperes, say plus 2 amperes. Yes, but this was a very brief spike, and then the current on the right coil, this part which is connected to the ammeter, it would suddenly go back to 0. And then when he opened the switch, the measured current would now spike to the other side. It would go to minus 2 amperes when it was measured, and the measured current on the right side would again become 0. So what happened was, you close the switch, the current spikes to plus 2 amperes and then immediately goes back to 0, stays 0. You open the switch, it momentarily spikes to minus 2 amperes and then becomes 0. So this was something pretty new and very weird that was happening. So Faraday actually was able to figure out what was happening. When the switch was initially changed from open to close, what happened was the magnetic flux inside the core, the B inside the core, it increased from 0 to some maximum number, right, which was some constant value versus time, right? So the magnetic flux inside it increased, and when the flux was increasing, it was changing. Yes, and that means that when it was increasing, there was an induced current on the opposite side. And similarly, when the switch was opened, the magnetic flux in the core started decreasing from the constant value back to 0. And a decreasing flux in the core induced an opposite current on the right side. So what Faraday figured out was that a changing magnetic flux inside a circuit or any closed loop of wire, it produced an induced EMF or a voltage within the circuit. And he wrote a law. He said that EMF denoted by this epsilon is equal to negative d phi upon dt. Yes, now in this equation, the phi is it's the Greek alphabet phi. It is the magnetic flux inside a circuit, and the epsilon is the electromotive force or EMF, which is nothing but a voltage source. So this equation now, it tells us that this induced voltage in a circuit is the opposite of the rate of change of magnetic flux with respect to time. The negative sign tells us about the opposite. Yes, now this equation, it is known as Lenz's law. Okay, I'll just write it over here. Yes, it is known as Lenz's law. So Lenz was the person, why do we call it Lenz's law and not Faraday's law? Because what Faraday had written was epsilon is equal to d phi upon dt. This is Faraday. Lenz was the guy who figured out the minus sign, and that is the more important part. So we know that what we know here is that the electric current is going to give rise to a magnetic field, as we saw before. But now, thanks to Faraday and thanks to Lenz, we also know that a magnetic field inside a loop gives rise to an electric current. So what we see here is that the universe loves symmetry, and Maxwell's equations shows some symmetry to us. So now we have the experimental result of this equation. According to Lenz's law, this is our experimental result. Now how do we go from here to here? How do we go from Lenz's law to the Maxwell-Faraday equation? Yes, so now imagine a very, very simple loop. Okay, a loop of current that looks something like this, a rectangular loop. Yes, a loop of wire, and it's got current in it. Yes, and very simple loop, and it has got a time varying B field inside it. So the B field, it looks like this. Okay, so when I denote it with a dot inside it, that means that the B field is coming out in the positive Z direction like this. So this is what I have. So now we know that rate of change of total magnetic flux is equal to the opposite negative of the EMF, right? Lenz's law, epsilon is minus d phi upon dt, which means the EMF is nothing but the electric force inside the wire. So the total magnetic flux, we can find it as the integral, the antiderivative or the integral of the B field over the entire area which is enclosed by the wire, isn't it? So the formula for phi is, according to phi of t is equal to integral of B ds. Yes, summation of the total B field over this area S. So I'll just call this area area S. This is the value of phi. So to find the total EMF induced across this whole circuit, yes, so I can use the right hand thumb rule. So the circuit I is going to be like this, the current in the circuit. Yes, this is my I. So to find the total EMF induced around the whole circuit, we sum up, we integrate over the length of the wire, right? And this is what we call a line integral. I think I talked about this before. So what we see is the EMF total, it's going to be equal to the line integral, which we represent by this closed circle of d epsilon, right? Total, we sum over the total, the each small contributions at each point. Yes, so we call those tiny contributions d epsilon, and when we sum over the length of the wire, we integrate, we get epsilon total. Yes, now recall the Lorentz force equation. Electric field is directly related to the force from electric charges. We know this, right? F is equal to QE. I guess we talked about this. And voltage is also defined as integral of electric field across a path. Yes. So E field, the electric field, is nothing but derivative of voltage with respect to distance, isn't it? So what we can say is, we can write E is equal to dV upon dl. Yes, so if we apply this into this equation, these two equations, if I combine, they are telling us that the small amount of EMF d epsilon at any point along the circuit is equal to the E field at that location, isn't it? Because d epsilon can be written as E dl. Yes, so I can write epsilon total is equal to loop integral of E dl. Yes, now I would ask you to recall an identity that we did in the very first video when I talked about the mathematics involved in Maxwell's equations, that integral of the curl, yes, of a vector field with respect to area is equal to closed loop integral of the same vector field with respect to length. Yes, now this is actually a theorem in mathematics that was discovered by a physicist and mathematician named Stokes. What he figured out is that integrating a field around a loop is exactly equivalent to integrating the curl within the loop. Yes, so this even makes sense to us because the curl is measuring the rotation of the field. So curl of a field within a surface is definitely related to the integral of the field around the loop that is enclosing the surface, right? Just think about it a bit more, and if you still don't understand it, accept it because it is true, and you might know how to prove it later on. So what this mathematical theorem is actually known as Stokes' theorem. Right, so now we are almost there. So what we have, our starting equation, that epsilon total is minus d phi by dt. Yes, and we have surface integral of surface integral of del cross E ds. Yes, which is going to be equal to minus d by dt of phi, which we just wrote as surface integral of b ds, isn't it? Which if I do a little bit of rearranging, I can get the derivative inside the integral sign, and I can write this as surface integral of minus db by dt ds, isn't it? Now if I eliminate both the surface integrals, what I am left with is del cross E is equal to minus partial derivative of B with respect to time, which is Faraday's equation, Faraday's law or Maxwell-Faraday equation. Yes, so what I did basically in this last step was I took the two integrals over surfaces, and I took the surfaces as we can choose the surfaces as whatever we want, right? So if we integrate both quantities over the same surface, they must be same, and that is how we got the final form. Yes, so I know this video has been very mathematics heavy, but it had to be. I could not make it any more simpler. I tried to, but I couldn't. So now the interpretations, this is going to be a bit friendly, I understand. So the very first interpretation, now Faraday's law, it has many important interpretations. So the very first interpretation is that electric current I gives rise to magnetic fields. Okay, this is a very important thing that we get from this equation. And magnetic fields around a circuit gives rise to electric current. So, and double underline, H gives rise to I. Yes, I gives rise to H and H gives rise to I. Yes. Now the second thing is the very statement of the law. What it tells us is B field circulating and changing with time gives an E field circulating around it. Yes, and the third interpretation is that circulating E field in time gives B field changing in time. Yes, so these are the three very important and very useful interpretations of the Maxwell-Faraday equation or Faraday's law. Now Faraday's law is very powerful because it shows us how much the universe loves symmetry. If a current is giving rise to a magnetic field, that means a magnetic field also can give rise to an electric current. And if a changing E field gives rise to a changing B field, yes, and a changing E field is also going to give rise to a changing B field. And when we move on to the last Maxwell's equation, that is Ampere's law, and when we look at Maxwell's addition to Ampere's law, we are going to see the next step of this symmetry. Changing E field gives rise to a changing B field, but does a changing B field give rise to a changing E field? That is what we are going to find out in Maxwell's fourth equation, and that is Ampere's law. So I will see you all next time. Thank you.